Hello everyone, and welcome to this video. We're going to be talking about a number of different topics, right? And here are some student learning outcomes. What should you be able to get? You should be able to understand and define acids and bases and correlate the strength of an acid to both its Ka and pKa value. You should be able to discuss the ionization of water and its dissociation constant, and briefly be able to describe the effect of pH on different biochemical reactions, and be able to understand an acid-base equilibrium in detail and write one yourself, and be able to derive and analyze the Henderson-Hasselbalch equation, which correlates changes in concentration of a weak acid and its conjugate base to the pH of the solution. And then you'll be able to interpret a titration curve. All right, so let's start with acids and bases. But first of all, why do we want to study those topics? How do they relate to biochemistry? Well, if you take a moment and think about biochemical reactions, most biochemical reactions take place in an aqueous solution, right? And an exception might be a reaction that takes place in the hydrophobic lipid bilayer. But aside from that, most take place in an aqueous environment or in an aqueous solution. So what we have a number of different molecules if we think about the cytosol or the extracellular fluids, which includes something like sodium, potassium, magnesium, chlorine. There's also a number of different molecules and macromolecules, all of which typically have ionizable groups, meaning something like a carboxylic acid or an amino group. And the ionization of those functional groups are directly associated with the biological processes that take place, right? So it's a really important topic in biochemistry is an acids and bases and the ionization of such groups. So we're going to start with the basics and define acids and bases. So one of the definitions that we learned about an acid back in general chemistry is that acids are proton donors, or they're also an electron pair acceptor, and we were able to appreciate the second definition more when we actually drew the equilibrium of an acid. And we can define bases as the opposite, right? They're proton acceptors and they're an electron pair donor. So if you think a base accepting a proton that lacks its one and only electron, so the base itself must be able to supply that lone pair of electron. So typically bases are electron pair donors, where in the case of an acid, it's donating a proton without its electron. So when the bond is cleaved, those two electrons go to the acid, so they're electron pair acceptors. So let's write an equilibrium of acidic acid. All right, so suppose you put acidic acid in water, right? So suppose water comes in solution. Well, now we learned about water being amphoteric, and it can act as both as an acid or a base. So in this case, how do we know, is water acting as an acid or is acidic acid acting as an acid? The strongest acid of the two will act as an acid. So let's think about it. If you deprotonate water, you'll get a hydroxide, and the negative charge is localized on an oxygen atom, whereas if you deprotonate a carboxylic acid group, the negative charge is delocalized around two oxygen atoms and stabilized by resonance, which makes acidic acid the strongest acids of the two, which now it can act as an acid. And acids are proton donors. So water deprotonates the acid, the bond is cleaved, those two electrons go to the oxygen, which goes hand in hand with the definition of an acid. All right, and hydronium ion is formed in solution, so I'm going to draw hydronium ion coming out, right? So in the case of a base, and that's an acid-base conjugate pair, right? If acidic acid is acting as an acid, the acetate in this case is acting as its conjugate base. So what about a base? Bases are proton acceptor or an electron pair donor. So let's take an example of ethylamine, right? And suppose it's in water. Now what's going to act as an acid and what's going to act as a base? The less electronegative atom will act as a base in this case, which is a nitrogen. And water will lose a proton, so it'll become a hydroxide. And we have the products, right? So there goes the product, and if you wanted to draw the actual mechanism, you can, right? Just draw out the bond between the oxygens and the hydrogens so you can actually draw the equilibrium. All right, so what can we say about those two acids and bases? Both of these they're really an example of a weak acid and a weak base, all right? And we know they're weak acids and bases because they only partially dissociate in solution, meaning what we have is in an equilibrium, all right? So we can actually measure the concentration of the acid and its conjugate base, or the base and its conjugate acid. So they have a measurable equilibrium. And what we see most in biochemistry are weak acids and weak bases. And they have a measurable equilibrium concentration of both the acid and the conjugate base. So those are weak acids and weak bases. So how can we define if an acid is a strong acid or a weak base? Aside from being able to look at it and know it's at equilibrium, so it partially dissociates, so it's a weak acid or a weak base. We can by its acid dissociation constant, which is really referring to the likelihood of an acid to lose a proton, right? If it's a stronger acid, its acid dissociation constant would be larger, meaning that the likelihood of that acid to lose a proton is higher. So let us talk about the acid dissociation constant. So let's define an acid dissociation constant. What exactly is it equal to? So if we think about the acid dissociation constant, and you recall that from general chemistry, it is equal to the concentration of the product over the concentration of the reactant. So in the product, we have the acetate. We also have hydronium ion. And in the reactant, we have the acetic acid, and we have water. Well, wait a minute. What's wrong with this equation? Exactly. Water. We ignore water because the concentration of water is kept constant. So in a dissociation constant, we do ignore pure solids and liquids because the concentration is constant. So the Ka value of acetic acid itself is 1.74 times 10 to the negative 5, right? Acid is 1.74 times 10 to the negative 5. And to avoid dealing mathematically with exponents of 10, instead we could take negative the logarithm of the Ka, and that would give us the pKa, right? So the pKa is really equal to negative the log of the Ka, right? And if you do the calculation for acetic acid, which has a Ka of 1.74 times 10 to the negative 5, you should be able to get a Ka around 4.7 or 4.3. All right. So we write it in terms of Ka value. That as the pKa value is lower, the acid we have stronger acids. So we could define the strength of an acid based on pKa value. And the smaller the pKa, the stronger the acid, all right? In other words, as the acid dissociation constant is large, it is more likely for the acid to lose a proton. And because its pKa is negative the logarithm of the Ka, then the smaller the pKa, the stronger the acids. In fact, very strong acids or strong acids that completely dissociate in solution tend to have a pKa value below 0. All right, so what about, that's the acid dissociation constant and hence Ca. So what about the base dissociation constant? Well, we determine it similarly to the acid dissociation constant, where we have that Kb. All right, well, that's the base dissociation constant. What if we really wanted to know its acid dissociation constant to be able to compare the conjugate acid of that weak base? Well, it turns out that the Kb is really inversely proportional to the Ka value. So if we know one, we can figure out the other. All right, so let's talk about water. What about water? If we think about water, although it is a neutral molecule, if we draw water, right? Although water is a neutral molecule, it can act as a very weak acid or a very weak base. So if you have water molecule and you write this association, two water molecules will give you hydronium ion and hydroxide ions. But this is really an oversimplification, because what we see in solution is that hydronium ion will be solvated with water molecules. So if we draw a hydronium ion, right, it's solvated by water molecules. So it's surrounded by water molecules. So let's draw some water molecules. Drawing them in a line, and we know that one of the intermolecular forces between water molecules that gives it its properties is hydrogen bonding, right? So we can have a hydrogen bond, here's another hydrogen bond, and here's a hydrogen bond, and so forth, right? Well, hydronium ion is solvated by different water molecules, and there's hydrogen bonding between the different water molecules. Hydronium ion, actually, that proton will hop from one electron to another, right? Something we refer to as a proton hop. And I'll show how it would look like on this image, but it happens at a frequency of 10 to the 15 per second. So it's very quick, meaning that now this proton will hop to this oxygen, and now we have, this becomes hydronium, this proton hops to the next oxygen, this proton hops to the next oxygen, and so forth. And that proton hop, which is characteristics of protons in water, or hydronium ions in water, occurs at a frequency of 10 to the 15 per second. All right. So sometimes we simplify that water equilibrium even further and write it out as water going into protons and hydroxide ions, although protons don't exist in solution on their own at all, right? So we can write, just like we wrote the acid dissociation constant, we could write the dissociation constant for water, but we specifically label that as Kw. So at room temperature, the water dissociation constant is equal to 1 times 10 to the negative 14, and the hydroxide and the hydronium ion concentrations must be equal. So each has a concentration of 1 times 10 to the negative 7, but that is dependent on temperature. So the human body, its temperature is about 37 degrees Celsius, and the proton and hydronium ion concentrations vary slightly. They're 1.6 times 10 to the negative 7. So at 37 degrees Celsius, the proton concentration, which is equal to the hydronium ion concentration, is really around 1.6 times 10 to the negative 7. Right? So here are some information about water and the proton hops. All right, so biochemical reactions take place at a very narrow pH range, anywhere between 6.5 to 8. So if we think about molecules that are common on the surface of protein, for instance, are carboxylic acids and amino groups, one which has an acidic proton, one which has a basic proton with a higher pKa value. So what happens is any small changes in pH can greatly affect those chemical reactions. So most biological reactions are actually carried out in buffer systems, and we're going to talk about buffer in a separate video. But the pH range is so narrow, and to be able to stay within the pH that narrow pH range, typically buffered systems are used. So we're going to end up talking about buffers and some of the important biological buffers. So we're going to end up talking about carbonic acid. We'll also talk about phosphoric acid on a later video, right? But that narrow pH range is so essential that any small changes can completely alter the ionization of such groups, which will alter the folding of a molecule. If we're talking about a protein, it's going to alter the intermolecular forces between that molecule and adjacent molecules. It can alter its solubility. It'll alter the activity of the protein, right? So we're going to be talking about that in more detail, but meanwhile, the pH occurs at a very narrow range, and that is greatly affected by the ionizable groups within a molecule. All right, so let's talk about an acid-base equilibrium. Some acids are polyprotic acids, and we talked about acidic acid, that's a monoprotic acid. It only has one acidic proton and hence only one pKa value. But some acids and bases are polyprotic, all right? And in the case of a polyprotic acids, the dissociation of that proton occurs in two separate steps, all right? And each step has its own pKa value. So let's consider carbonic acid. Right? So all right, so let's consider carbonic acids. Carbonic acid loses one proton, right? One proton is gone. It becomes bicarbonate, and then it loses yet another proton to become carbonate. All right, so let's write it out. All right, so you have carbonic acid, it becomes bicarbonate, and then it becomes carbonate. And in each step, it's losing a proton. So we write its dissociation, or its acid dissociation as two separate steps, each which has its own pKa value. So we're going to start with this. All right, so those would be the two equilibrium. Each of the two has its own acid dissociation constant, or its own pKa value. Based on what you know, which one would you expect to be the most acidic proton? The very first proton or the second proton? Correct, the first proton. And in fact, it has a pKa value of it has a pKa value of 6.3. Bicarbonate, on the other hand, has a pK value of about 10.3, all right, roughly. So if an acid is polyprotic, having more than one acidic proton, its most acidic proton is labeled as pKa1. Its second acidic proton is labeled as pKa2. The stronger the acid, the lower its pKa value, meaning that the first proton is more acidic, more readily lost, right? Its proton is lost. All right, so the smaller the pKa, the stronger the acid, the more readily the proton is lost. So that's an example of the... All right, so let's ask ourselves, how do changes in pH actually affect the ionizable groups within a molecule? What would be the charge of a molecule at a given pH? Or how do changes in concentration really alter the pH of the solution, right? Alright, so now we're going to try to derive and analyze an equation that allows us to quantitatively be able to correlate concentrations of a weak acid and its conjugate base to the pH of the solution. So we're going to take a simple example where we're going to use that we have an acid, right? A is for the acid and H is the proton it will lose. Alright. So you have an acid, the acid dissociates into its conjugate base and a proton. And if we write the acid dissociation constant, if we're interested in correlating the concentration of the acid and its conjugate base to the pH of the solution, we can, because now we know the acid dissociation constant, which is a constant for a given system. And if we take negative the log of the proton concentration, that would give us the pH of the solution, right? So we're going to take negative the logarithm of this equation. All right, so if we take negative the log of both sides, we get that, and we just separated the equilibrium between both. That way, negative the log of the proton concentration is equal to pH. So we're going to solve for pH first. All right, so if we rearrange the equation, we get that the pH is equal to the pKa plus the log of the conjugate base over the acid. All right, so that's what we refer to as the Henderson-Hasselbalch equation, where pH is equal to pKa plus the log conjugate base over the acid. So let's take an example. What if the concentration of the acid is equivalent to the concentration of the base? And let's just suppose it is 1 molar. So the log of 1 is basically 0. So when the concentration of the acid is equal to the concentration of the base, the pH of the solution is equal to the pKa of the acid, right? A concept that we'll touch back into in quite a bit of detail when we talk about buffers. So now we're going to discuss titration curve in terms of the equilibrium between carbonic acid and bicarbonate. All right, so it has 2 pKa values, and suppose you have carbonic acid, and you put carbonic acid, or you start titrating base into carbonic acid. The very first proton will dissociate, and then the second proton dissociate. And to take a look at a titration curve, what we have is basically, so if you're titrating a base, what you have is the equivalence. You could think about it in terms of the equivalence of base added, how much base you add, right? When you have one equivalence of base to the acid, one of the protons will completely dissociate. Or you could think about it in terms of the equivalence of the proton that dissociated. Right? So in other words, we're looking how many protons dissociated, or we're looking how many equivalents of hydroxide ions we're adding in solution. So that is against pH because we're titrating, so we're changing the pH of the solution. So, pH. All right. Well, it has 2 different pKa values, right? So it has 2 acidic protons. So we're going to need 2 equivalents of base to completely deprotonate the acid. So here's 1 equivalence of base. Here is 2 equivalents of base, and I'm just going to write the third one, right? And once you hit the first equivalence of the base, that's when the acid's completely turned over into its conjugate base. And that's when you see this really sharp increase in pH when a small amount of acid is added, right? Well, the pKa of the solution does relate to the pH, right? Where the pH range for a given solution is plus or minus 1 its pKa value. So that's what we get at one equivalence, that the acid completely turned over into product, all right? But when the concentration of the acid is exactly equivalent to the concentration of the base, recall in Henderson-Hasselbalch equation that the pH is then equal to the pKa, and that takes place at the half equivalence point. So at 0.5, at 1.5, and we don't have a 2.5 really. So at half the equivalence point, the concentration of the acid and its conjugate base is exactly the same, and that is correlated to the pH of the solution. So at about 6.2, that's when the concentration of the acid and the base are exactly the same for the very first deprotonation. For the second one, it's at 10.3. Right? So those dotted lines are when the pH is equal to exactly the pKa. Well, that range is a plus and minus 1, right? Within a plus or minus 1 of the when the pH is within plus or minus 1 of the pH value, those are basically when a plot is somewhat leveled off. So we're going to actually show that. So between 6.3, so 5.3 and 7.3. Within that region of a titration curve, the concentration of the acids and the conjugate base are somewhat similar, right? When the pH is within plus or minus 1 of the pKa value, there's small changes in pH, right, upon the addition of an acid or a base. So now we could draw the titration curve. Initially, the solution is acidic, and as you start adding, the solution starts to level off, and once you hit the 1 equivalence, the concentration of the solution changes dramatically up until you hit the second equivalence point. So a titration curve for something, for bicarbonate really would look something like that. All right? And we'll talk more about titration curves on our next video.